Morning.
Oh, good morning.
Morning.
Oh my God.
How's everybody this morning? Am I talking? Yep, I am. Can you see me? There I am. Hi. How's everybody this morning?
Coherent.
Yay. It's hard, isn't it?
It is lately, that's for sure.
It's just hard. I woke up pretty sure that it was weekend still, but then I thought, wait, I don't think it is. So I remember. You guys are doing so good. My goodness. Let's do some stuff. I'm going to turn this off. Isaiah's normal. Any questions this morning before we get started? I posted that magic square code, which was kind of complicated. So I wanted to give you a chance to see that. They have some pseudocode for that in our textbook. If you have a chance to run that code in that visualizer website, kind of experiment with it, use it as something to play with over the summer if you like, and kind of manipulate it and change it around and just basically see what it does. I think that'll be a good exercise, a good activity, good practice. So we need to keep practiced up over the summer. I hate to say programming is like riding a bike because, you know, I was like the last kid in the neighborhood to be able to ride a bike, and I have forgotten how. And if I get on one, it's pretty ugly. But I had that hip replacement, and the doctor told me not to do that, thank goodness. The visualizer said it was too long to run. Oh, no. Well, we'll have to see if we can get debugging established in Atom then here in our last couple of days so that you guys can step through that code if the visualizer won't let you use it. That's a shame. What we have left really are two topics that are pretty big, but they're just introductions to the topics because we're in Introduction to Programming, and you guys have actually learned a lot for an Introduction to Programming class. Remember that as you move forward, that this was your introduction, not your be an expert, know everything kind of class. That's a great thing about programming, always lots more to learn. So I think that's why it's an exciting field, because there's always more that you can learn. You can always figure out a new way to do things, even if you've figured out an old way. So the last two topics that we have are working with data files and object-oriented programming. And that is quite a bit. So we'll just be looking at an introduction to each of those topics. And then our last assignment that has to do with glitching an image will kind of use both of those topics together and come up with something that's kind of neat for us to do. And that one is due Thursday. So I hope to get to a little bit of it today, but don't worry if you don't know how to get started on that, because we'll definitely spend our time on it on Thursday if we don't get to today. So today I'm looking at all these presentations. That's why I might not have time. So I'm going to start with the Chapter 10 PowerPoint from our textbook. So this is in our modules section on Canvas if you want to grab it, or else we can just look at it together. I think it would be nice if Zoom had some sort of icon to show me I'm sharing. It does so well with some things, but then not with others. So you can see this, right? I am sharing. Sometimes I'm not and think I am. So sequential data file. I have another presentation. Okay, thanks, Isaiah. I have another presentation because, you know, I just can never have enough. Sometimes I feel like I need a presentation to be able to explain something to my husband because I'm so used to having them to help me. But I do like the visualization, even if PowerPoint isn't the greatest technology. So lets us visualize some things. So I have another presentation that I'm not going to show you, but in it I have two pictures. One picture of a VHS tape. Does anybody remember those? I know some of you do. I know we have some Disney movies on VHS. We have those black label Disney movies that are supposed to be worth like, you know, $10,000 only. Unfortunately, they're not. Have you heard those stories?
What's a VHS?
VHS is like an old tape, like before DVDs. Do you remember when you were little? You might not have ever had them. I'll find a picture. It's
I remember DVDs.
You remember DVDs, but not VHS, because they're kind of before. Let's look. I'll find a picture here. So here's a VHS tape. So we, like I was saying, we have a lot of these Disney movies. Yeah, one for holding the tape and one for recording it. So it's like Guardians of the Galaxy. You know how Guardians of the Galaxy, he has that cassette tape from his mom. Do you remember that on Guardian of the Galaxy, right? And so a VHS tape is a lot like a cassette tape like that. It's just it did video. Betamax was really old. I had a few years ago to get rid of hundreds of those. My husband kept saving them because they had these weird old movies. Oh, it's awful. So obsolete technology, it's awful. It's hard to get rid of. It's around forever. RJ, don't go there. Okay, so this is a VHS tape. It's old sequential technology, and that's all I wanted to say about it. But it's important for us to have this kind of historical aspect. Sequential meaning I had to read this tape from the beginning to the end. I couldn't just jump around to a specific spot. So, and no, we're not going to make a Turing machine. You guys could do that over the summer. You should get together. See what you can create.
Oh, come on. We're not that old.
See what you can create. It's all new, right? What's old is new again, especially if you're creating it over. But you don't want to recreate VHS tapes because they were really bad and you had to fast forward to get to the place you wanted, and super sequential. Just no fun at all. So if I look at a DVD, which again is obsolete technology, but if I look at a DVD, they were different because I could directly access a specific point. They offer direct access. So a DVD gives us the kind of access we get with a database. So we like that, right? We like to go directly to a specific thing. So these old technologies are important in understanding what our limitations are. If I'm working with a text file in Notepad or anything like that, or reading that text file in my program, I am limited to sequential access. But because that text file is sitting on a hard drive, I could also access it as though it were a binary file, kind of like a database, and I would be able to go to a direct point in that file. Now, sometimes we have backups still on old tape devices. So in that case, we wouldn't be able to access something directly. But we can kind of think about these two different access methods as defining the two main types of files that we use. We have text or sequential type files and binary files or direct access files. So we might have different programs that create these kinds of files. One thing that's important for us to remember, though, when we're working with computers is everything's a file. right? And sometimes I can confuse people at the beginning of the semester that way because your source code is a file and Python is contained in a file. And when you run, you can save your output to a file, and we save pictures in files and we save videos in files, and basically everything's a file. It's just the way the program reads the file that matters, right? So I could, with our Python code, I could open a video file. I might not know how to process it correctly, but I could open it and try to read it. So what I want to do, though, is open and read files that I can understand. So when I look at a text file, that's usually something that a person could read. I could open a text file. I can see all the rows or records in that file. It only contains ASCII characters, things that are in our ASCII code set. Those binary files, though, could have special codes. All right. So again, each of those kind of lends itself to a certain access mode. Binary files are things that are usually compiled. So computer languages, source code that's been compiled into an object code would be a binary file. Our database type files that our database management system knows how to read and write. When we use text files, it's easier for us, though, because we can actually read those. So we can display them and make sure that everything's the way we want it to be. And they say they're universal. We can pass that text file to somebody else, and they don't have to have any special software installed to properly read that file. Okay, so whenever I'm looking at a text file, I'm usually looking at rows of data. So I'm going to keep track of something in a text file when I need it to be persistent. In our program so far, we run our script, our Python script, we enter data, we process it, and then we're done. That data just disappears, right? It's not retained in memory, it's not saved anywhere. So we would like to be able to save data to make it persistent so that the next time we run our script or our program, some data is already there. We don't have to re-enter everything every single time. In this example, they'd like to keep track of some information about some customers. And we're going to keep track of 3 things about each customer: their name, their address, and their phone number. Each data item like this, each variable, when it's used in a file, is called a field. So I have the name field, the address field, and the phone number field. So a field is kind of interchangeable with a variable. It's just that it is associated with a record. And a record is the information that we're keeping track of for one customer. So let's see, they should have a picture here. It's not exactly the customer that they were talking about. Let me backspace. Here we have some different fields in a text file. We have a student name, a test score 1, test score 2, test score 3, test score 4. So we're keeping track of some test scores for different students. So each student has their own row in our text file. That row is called a record because it's in a text file or in a sequential file. Again, each of the columns in our file is considered a field. So the whole thing is a file. Each row is a record. Each column in each row is a field. So the field is the smallest thing. Now here's our little data file again with its formatting that we know, so we know what each thing is. But a lot of times we will save data in a text file in a comma separated manner so that the next program that reads in this text file knows that each different field is separated from the next field by a comma. So our Abrams row looks like this as we print it out in our program, but internally in the text file, we see the name field, a comma, and then the first score and commas separating each of those fields. That's a CSV, or a comma separated value file. The CR, or carriage return indicator at the end, is our new line control code that we've used when we've been printing output. We've used that \n to say go to a new line. We have to do that same thing within a text file to say we're done with this row. Here's the end of that row. They call it, in this particular instance, a carriage return, and it goes back to old typewriters that we would have pressed the carriage return key, which is where the enter key is now. So our enter does it to us automatically. When we're typing like in Word or something, we press enter, it automatically does that carriage return and takes us to a new row. So we keep bringing this up, sequential files and direct access or random access files. It matters because it really affects how we process our data that's in this file. If I'm reading a sequential file, a text file, I'm going to read each record, each line in that file, and I'm going to process each of those lines. I'm going to probably do the same thing with each one of them, right? Like, for example, for our test scores, I'll read in the first student's record. I'll add up all his test scores and divide by 4 to say the average is, and be able to calculate the average. Now, the problem with this sequential file is, again, I have to move through the file in an organized manner. Start at the beginning, move forward. If I want the 50th record, I have to read through or scan past the first 49. Now, direct access file takes away that overhead, lets me go find a specific location in a file. But I better know what my file management strategy is, or I'm not going to be able to find that specific location, right? So direct access implies a little bit smarter of a read and a write. So I have to do these certain things. So if I wanted to create a file on disk, I would have to open it. And when I open a file, I have to tell Windows or Linux or whatever operating system I'm using what the name of that file is. And I need to specify the full path name. Like, if I want it to be on my D drive, I would need to specify the D drive letter, and then all the folders I want to use and the file name. As I mentioned, you'll get a lot deeper into this in some of your other programming classes, and we have some good examples we're going to look at here in a minute. Now, the external name of that file would be that full name on disk that the operating system knows. Internally, in our program, we're going to have a different name associated with that file, and that'll give us something a little bit easier to work with. We're also going to specify how we're going to handle this file. Are we going to read it in as input, or are we going to update the file and write it out as output? With a sequential file, we can kind of do one or the other, right? We're not really doing direct access where we can say, oh, I want to read this record and update it and write it out. Now, this is the kind of files that could be being handled with the IRS and some of the checks that are coming out and stuff, right? They keep mentioning, oh, these are really, really old systems. That's why things are taking a long time. That's why they're problems. They're doing sequential file processing, right? They're having to process things in a certain order. So people were saying, are they doing things alphabetically? We don't know. What kind of order are they doing it in? Well, it does matter, because if we're working with, millions of rows here, millions of people, then we have to process them one at a time if we're working with these old style sequential files. So it's very important to us in this day and age too, to know that this is going on, because it impacts the way that we handle our file processing. Hopefully this will be an obsolete technology soon, and you guys won't have to teach people this later, but for now, it's not. Now, we open that file is input or output. If we opened it for output, we're going to start writing data to it. When we're done, we're going to close the file. Make sure it's saved by the operating system. Now, if we are opening that file as input, then we're going to read data from it. When we're done, we're going to close it.
So one would assume that if you're converting a sequential file to a direct access file, you have to go one row at a time to do the conversion.
Right. So you might have some sort of mass load program or something that, can do 500,000, but internally it's doing it one row at a time. Right. And so I don't think that text files will go away per se, but we use text files that have more intelligent formatting now, like XML files and things like that, that allow our code to access chunks, chunks again of data instead of one row at a time, like this old sequential access. Yeah, so I just think this sequential file access is something that is becoming obsolete, because usually people read, even an entire text file all in one big chunk and process that as an XML data file or something that gives us a little bit more control, if that makes sense. So you'll see that as you get to the more advanced classes, that just like in today's world, you probably wouldn't create a console program. You wouldn't create a Python program that asks for console input and console output like we did. You probably won't do a lot of sequential file processing, but these are all really important basics, cornerstones, foundational knowledge to know.
Isaiah's got a pretty good question.
What's that?
Isaiah's got a pretty good question about physical memory.
Yeah. So to me, it's just sequential that is less important than it used to be. So we'll always use Notepad, we'll always use text files, but in our programs, we'll be able to process them more as chunks of data instead of just a sequential processing. I don't see it very often in textbooks even, so. This is actual, good question. This is actual physical memory. So if I'm writing a text file, it's gonna stay, it's persistent, right? It's written to a drive, be it a hard drive or, whatever kind of media it's been saved to, it's persistent. Does that make sense?
Mhm.
Just that our newer file accessing methods let us get away from this, open, read, close type strategy. Yeah, with our virtual memory and, just random access, using databases, using XML files, we have more control. So one thing that's really important that a lot of people are not super clear on is what happens when we close a file. So yeah, they all use RAM, but RAM is our temporary memory that we use while the computer is up and running. And if we want to save data for over a shutdown of the machine, then that data has to be written to a more permanent storage, like a hard drive or a solid state drive. So RAM is our temporary storage. Disk is our permanent. Does that make sense?
Mhm.
Okay, keep up questions, good. Now, when I close a file, I'm actually saving the information to the operating system that the file was created or updated, and we're really writing an internal end of file marker to the end of that file. Just like we wrote a control code, a new line code at the end of each record, we really are internally writing an EOF marker at the last record, but the operating system takes care of that for us. So we don't have to do that. But if we don't do the close of the file, that doesn't properly happen. So we'll try that when we are experimenting. I know I can't type, I can't speak, can't do much. Too much rain, need better weather. Too much Facebook for me. It's looking at all those people that can't speak right. I gotta stop. It's a terrible thing. All right, so here is an example. We have this non-language example here. It's not any actual programming language. It's not actual pseudocode. It's sort of just an example. We would say open the file name grades. So that's the file in our file system. For output, so we're saying we want to write this file. And then the last thing is the name we want to refer to this file as in our code, which is as new file. So we've got all of this information here. Our program is going to refer to this as new file. We're going to write to it, and the operating system knows this file as grades. Now, when we close that file, our end of file marker will be placed, and the file is saved. If we want to read a file, we wouldn't change much there. We would be saying that our access mode is input instead of output. They changed the internal file name to grade file. And now they're reading the different fields. Whenever we're reading a file, we usually have to go into a loop and continue to read rows from our file until we get to the end of the file, the EOF marker. This is just the same as prompting our user for input from the console and then asking them for a number or a special word to stop. While we haven't received that special character, we're going to continue prompting them. So when we're working with a file, we're just getting our input from the file instead of getting our input from the user. We could still ask the user for input. There's not a rule or something that says we couldn't, but in general, our data is coming from the file now. So we'd go into this loop, read and process all of the rows in our file, and then close our file. Here's some pseudocode where we're actually prompting a user, and then we're taking that user's input and writing it out to a file. Take a second to look at that one. We're only outputting a student and a score. Our output file is named grades, and we're going to call it new file in our program code. We're going to prompt for a name and a test score. And we're going to ask them to enter 0 for both when done. So we do have that sentinel value that's going to close our loop. We're reading in the student and the score, and if the student is not equal 0, we're going to write to our new file, student and score. So this syntax, this write syntax is going to be different for different languages. Then we're going to prompt for a new one, read it, and continue our loop. If they gave us good data, we'll write it out to our file. Otherwise, we'll end our loop. Once our loop ends, we'll close our file. Now, a lot of programming languages give us the ability to check for end of file in different ways. We might actually have an EOF or an end of file function. And in that pseudocode they gave us, they were assuming that there's something like that. So we were saying, while we are not at the end of the file, continue processing the file. So if we have an EOF function like that available to us in our programming language, we're going to see that probably in the test condition of a loop, so that we can process the file until end of file. Here we're reading our grade file that we created in that last pseudocode. So we've created that file based on our user input, and now we're going to read it. So we're opening it for input, calling it grade file, and while we are not at the end of the file, we're going to continue reading it. Read it, write it out to the screen. So this time, instead of just reading our user data and writing it directly to the screen, we read our user data, wrote it to a file, and now we're going to read that file and write it out to the screen. So just that intermediate step of making our data persistent so that it's always there. Now, even though we're reading, we still need to close that file. The operating system needs to know that we're done with it. If somebody else wants to update it, they can, because they can't if we have it open. Now, what kind of updating might they want to do? Well, they might want to not write out a record to a new version of a file. They might want to change one of the records or add a new one. So what we would do in that case, we are reading a file as input, but we also want to revise it. I told you it's sequential. We can't do that. We've got these limitations. We're under these rules of sequential file processing. So all we can do is read the input and create a scratch file, a dummy file, a temp file to hold our output. Then when we get done, we will have our new file in that scratch file. So we'd have to do some renaming and things, right? It's kind of messy. Now, as we were doing that, the processing that we would do, if we find a row or record that we'd like to modify, we will just make the change and write that out to our new scratch file. If we find a row that we'd like to delete or record to delete, we just won't write it to our output file. If we want to add a new record, we'll write it. And of course, we'll be writing all of the other records that we don't want to change. Then when we're done, we'll delete that original file and rename our scratch file or copy it over to that original file name. Messy, messy. In this example of pseudocode, they're doing that sort of thing. Every student that's not equal, the one we want to delete, is going to be written out to the file. The one that does equal will bypass that write statement, so it'll end up not being in our new file. Sometimes thinking about how to do sequential file processing is a really good logical exercise, because you have to be really logical, and sometimes it doesn't cooperate. Again, Here we're looking at modifying or copying a file to a temporary file. We're just reading our input, our source, and writing our target. So this is the same net effect as copying a file in Windows, but we could do that programmatically. In this example, they're just modifying one field in one record. We're looking for a specific student name, and we're going to output their new score instead of their old score. And this kind of processing here is pretty rough compared to working with direct access files that we usually get to work with nowadays. As you see here, we're having to create a completely new version of the file because of this minor change. So just to update the name in one student, or this one score in this one student record, we have to create a whole new copy of this entire file with this one revised score. So it can be a little bit tedious, but we can get it done. Here in this code, we have a row or a record that we would like to insert into our file. So as we process our file, we're reading it and writing out the new one. And then we finally get to the spot where we want to insert our new row. We write it out, and then we go back into another loop to continue reading and writing our file. So kind of complicated. So if I'm processing someone's federal return and I've copied the entire old school database that they do have out to tape, because that's how I'm going to handle it, this is what I would have to do to update anything. What a mess, huh? Long. So it can be quite tedious. But we can make it a lot easier. We could use arrays within our code. So what if we just had one array that we read everything into, and then we did all of our updates and inserts and changing of data and everything in that array, and then we could just write that array out to our new file. That would make it a little bit easier than going into all these multiple loops and things. So whenever we have one construct like a data file, we might be able to ease our processing by using another data construct like arrays. And this is kind of just reading our file into a temporary location that gives us direct access, right? Because we can go to wherever we want in our array and update whatever student test score they want updated. So this example, pseudocode attempts to do that kind of thing. We're setting up several different arrays, 3 of them, and a count to keep track of where we are. We're going to read our data file, right, and update our counter. And we're putting the data file into our student array and our test1 array. So we have one array keeping track of the student names, one keeping track of the test score, and then test2 is going to be our updated test score. So this actual pseudocode would just allow us to update test scores for whatever students needed to be updated. After we were done, we can go into a loop and output all of our students with their new test scores and their old test scores, or however we wanted. Now, another concept that's important when we're working with sequential files is merging files. So let's say I have a file, a sequential file with a list of people from Kentucky, and I have another sequential file with a list of people from Minnesota, and I want to merge those together by last name so that I know where all of the Smiths are. When I do that, I have to read both files, and I have to be concerned about which one is greater than the other one. For me to do that merge, those files would already have to be in sequence by last name so that I could read them properly. I'm going to have two files as input and one as output. When I read from file 1, I'm going to compare that last name to the last name that's been read from file 2. If file 1 is greater than or less than, depending on the sort I want to output, I'll output it to our new updated file. Otherwise, I'll do file 2. Now, whichever one I output, whichever file I output, I need to read from, and I'll do the comparison again. Which one is greater than the other? Which one should be written out to the file? When I'm done, I'm going to close all 3 of them. But that merge process is something that's still a very important algorithm for us. So here's some kind of code, pseudocode-ish, for a merge. Read the first record from each file, which one is greater or which one is less than, to determine what I output. Merging. So here they have an example, the big merger. They have 2 payroll files and they want to merge them into a single file. All of the records are ordered in increasing order by employee number, and the last record in each file is 000.0. The 2 files are going to be merged into a new file called payroll. We have some variables we need to keep track of. We're going to open all of our files, read our 2 files, then determine which file needs to be written to our output file and read again. Once we get done, we're going to close all 3 files. And here they even have some sample data for us. We're not going to try to write that one based on that pseudocode. It's pretty general. Now, one other thing that we might need to do when we're working with data that's sequential and in a given order is set up a break condition. And we see this all the time. If you get on your bank's website and you look at your account, a lot of times you'll just see the activity so far this month. And if you want to look at previous activity, you'll have to ask for a previous statement. Just click on that to ask for a previous statement. That's because the bank does processing at a given point in the month, and they end all of the processing for all of the previous transactions that have occurred and start a new, like, general activity. And whenever we do that, that's a break, right? We might have other control breaks that would be important to us besides month. We might want to sum all of the test scores for a given student. We might have several records for a given student, and then we would break by student. Or we might want to count students that have degrees in different programs, right? So we could be looking at every student with their degree program and say, if it's CIS, add 1 to the CIS total. If it's, some other value, MTH, add 1 to that total. So then we would have a control break based on the degree program. So that's a common thing for us to do. And if we did that, our degree program then would be the control variable, how we want to control our output. We see it often with months though. Let's look at Runestone and write a quick file. See if we can do this. Okay, we're going to try this in Atom, but there have been times I've had to go back to idle because Atom, we may need some additional like extensions or something to handle file processing. I'm looking at Runestone Academy and I'm going to go to section 11 files because they have some really nice examples for us to use real quick. And they just give us the same kind of information as we just saw in the presentation, but now it's Python specific. So let's see, I've got Atom open here with all sorts of programs open. I'm going to close those. I want to create a new file. And I want to save this. I'm going to save this in my Python folder, but I want to create a new folder. So I don't want to just save this right in my Python folder. And I'm just going to use the save file dialog box to create a new folder in here. And I want this new folder to be file processing because I want to keep all of our stuff in one folder. Okay, so make sure you save this new Python file into its own folder. File processing will be mine, and I'm going to name this example 1.py. And that's not going to be a super good name, but I want to just get something out there. So I have my Runestone example here. My Atom doesn't want to come back over. There it is. And I have my example here. Now, whenever we're working with Python, they say that when we want to open a file, we use the command open, and then we say file name, and next, we have an argument that specifies how we want to open that file, what our mode is going to be. Are we going to be reading it as input, or are we going to be writing it as output? When we're done, we're going to close the file by, again, using a close. So that still doesn't really give me all the information I need, just the name of the functions that I have in Python. So let's go ahead and go to the next. Now, in this section, they're talking about file names. And depending on your background with command prompt, and when you're working with files and folders, it can be something that is very clear to you that you've used a lot, or it can be something that's a little bit confusing. This picture down here, this sort of textual graphical, is showing you a file structure. So I have a folder named My Files. Inside the My Files folder, I have another folder named Other Files, and then another child folder called All Projects. I know those are both in My Files because of that line. Now, in my Other Files folder, I have a folder named Extra Data And inside it, I have an actual text file named data4. In my all projects folder, I have a my data and a my projects folder. Each of them have a few items, a couple text files, a Python file, and a text file. We're concerned about the path name to these files. If I am in the My Project folder, my Python program is in that same folder, right? Then I can just refer to the file data1.txt as data1.txt. I don't have to worry about what folder it's in, what hard drive it's on, what drive loader it's on. None of that path information matters to me because my program and my data file are in the same folder. That's how we're going to do it. That's why I wanted to create a new folder. Now, if I want to, however, from my Python program here that's in this My Project folder, if I want this program to be able to access data2.txt, I could use a path specification that included the ... parameter. ... means parent. So that says from where you are, my Python program.py, go up to the parent. All right, my parent is all projects. And then from all projects, go to my data, okay. And then in my data, you should be able to find data2.txt. Same thing for if I want to get to data3. Go up one, so I'm in my files, parent folder, then go into, oops, sorry, hang on. I was doing this last one. For this last one, we're here. We're going to go up a parent. So now we're in all projects. Then we're going to go up a parent again. So then we're in my files. From there, we're going to go into other files as a folder, then extra data, then data4.txt. Now, those kind of path structures are all relative file names. They are relative to my current location of my Python program. Sometimes I might see somebody say, well, I want to put in a full path name like this one that starts with a slash. It says, go to the users folder, go to B. Miller and my files and all projects and blah, 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 blah. Well, since this starts with a slash, that means it's an absolute path name. So it will only work for B. Miller on this machine that has this users folder. So this is a really poor way of handling it. We want to use relative path names so that we can find our file, no matter whose computer we get copied to. So path names and file names, for our use today, we're just going to try to keep everything within the same folder so that we don't have to worry too much about paths. That's stuff for that CIS120 class, right? Talking about all those path names. Okay, so here's a data file. We have this big data file. What in the world is it? Let's take a look. Our data file is information about NFL quarterbacks. So here are the fields we have. First name, last name, position, so that's this QB thing here. Team, here's our team, that's Cleveland, right? Then their position, oh wait, team, then completions, attempts, yards, touchdowns, interceptions, completion percentage, and rating. Okay, so here's my file. Notice it's not comma separated values, is it? These values are separated by spaces. Let's copy it. Are you here? Can you find this place? Let me give you this URL. Post it in the chat. in case you're not here. So I want to copy all of this data and create this file. So let's select it and copy. Let everybody get it copied. Now in Atom, I just want to create another new file. New file. I'm going to save this. And I want to save this in that same folder I just created, file processing. And I'm going to name this one qbdata.txt. Adam doesn't care, right? We can make it computer code or text or whatever. I'm going to save that. And then I'm going to paste. Okay. Now I should be able to save that. And I can actually close that if I want to. My QB data. I don't want to hide that. I want to bring back my view over here. There it is. I'd lost it. I had tried to maximize my screen space and couldn't find my folder view. I'm just going to make sure that I've got these things in my folder. I know, I couldn't find it. I think I have too many things up there. Good. All right, so we have our file. Now, they're giving us some information here. Let's try this. And I'm going to put in a basic comment. And they say we can say our file reference, how we refer to this file in our code, is going to be set by opening our QB data file. And we're going to open that file for read. Oops, that should be a comma, not a period. And then they say we should just be able to close it by saying, however we refer to that file, which we called it file ref, go ahead and close. Let's run that. And I just want to run that and make sure I don't get any errors or anything. Looks good, no problems. So we were able to open our file and close our file. Everybody okay? That you open it and close it? Because if it didn't exist, we'd have a problem. Okay, now let's use our file, our QB data file, as input to a program that will do some processing. And they actually kind of have an example for us, but let's think about it before we look at that example. We are going to read each line of the file, all of that quarterback data, and then we're going to print it out with some additional information. And because our sequential file is a sequence of lines of text, we can use a for loop to go through the file. Remember, a line of a file is a record, and that new line character, or \n, kind of indicates that it's the end of a record. And then we have the EOF marker that shows it's the end of the file. Okay, so let's try this one here. They don't want us to call this file ref. They want us to call it in file or QB file. What do you want? QB file. So I'm going to change it in both places. QB file. So that file reference, I can change. I can make that be whatever I want it to be. And that's how I'm going to refer to the file in my program. So I can use a for loop and say for each line in that file, I want to set up a little array called values that hold each of the fields. So we just saw last week or so that we could use this split command to say we wanted to split something by a certain character. Well, we want to use spaces, so we can leave the parameter or the argument blank, or we could specify a space if we wanted to. So now we're going to have values, whoops. Values is going to be a list of the different fields. Sorry. Try to spread that out as much as possible. So we're reading in that one whole row of that quarterback data, and we're splitting up that data based on the space character, saying each of those things is a different field. So now let's print out some stuff. We're going to print out, they want QB, and then a space. And I'm going to go down and say the next thing we want is the first of our values or fields. And then we want the second value or field. And after that, we're going to say had a rating of, and then we're going to add the index value 10 field, or field number 11. So I'm going to change my print statement formatting, hopefully, to something that's a little bit less squished, because I could push all those things together on one line, but it would be hard to read. So I'm going to separate it out into multiple lines. And then I'm going to close the file. So let's think about this here. First, we open our file for input with a read. Then we're going to read and process each record in our file. Within our loop, we're going to split up our file row or record into its fields, output some information about them, and then finally close our file. So let's see if we can run this. Ah, there's all of the, I'm missing something. I've got QB and then had a rating of, some of them have ratings. I have some extra spaces. We have some extra spaces because we use these commas instead of pluses. Is that what's wrong? What's wrong? What else? The file itself has extra spaces at random. Oh, let's check. Yep, there's some. So if we go back and change our split to get rid of the space character, does that make it work better? Is it more flexible that way? Let's see. So when I put the space into the parameter, the argument, then it would only work with one space. But when we leave it blank and let Python take care of it, it says, oh, I don't care how many spaces there are. That's just the in-between two fields. Does that make sense? So we're not as concerned about how many spaces are in between if we let Python take care of it. Now, I also could get rid of the comma in the print. But if I do, then I'm going to start running into trouble where I need to convert to a string and things like that. So I'm just going to change my mind there and leave it with the comma. So we have some interesting spacing, but that's okay. So pretty fancy here, pretty fancy processing. We're reading a file, we're splitting all of the values into individual fields and processing that information. Now, when we let our for loop take care of this, notice that we didn't have to do any actual read statements. It's all taken care of for us. Python is doing its awesomeness in its for loop and saying, oh, you hit the end of the file, there's no more, you gotta stop. But we could end up having to take care of that ourselves. Let's open a new Python file. And I want this one to be let's make it readline.py. So we're going to take care of reading our input ourselves instead of letting Python do it in a for loop. Awesome to let Python do it, but maybe that's not enough for us. So let's set up our input file, qbdata.txt, and we want to open it to read. We can set up a variable. They call it a line. Let's call it a record. We know what these things are. And we're going to say that we want to read a line from our input file. Now that line is in a record. Let's print it. And then I'm going to put in the close. And file dot close. I'm going to run. And then we see our first quarterback's data when we printed that record. So that's the line that we read. Now, what if we want to read more than one line? Here we did read line. We could actually say read lines. Let's try it. What is the difference? Ah, a whole bunch of difference, huh?
Huh?
So now we got all of the lines in our file.
Oh, this one's still going.
Do I? So now we have our A record array has lines from our file. So Python makes it super easy for us to read all of the lines into an array. So we can do a lot of different reads when we're working with Python. Read just one row, read all the rows, read all the lines all at once, and then we can write some things out.
Should we be putting these in our quick reference sheet?
Yeah, I'm looking at, let's do that before we look at the writes. I think that would be a good time. So I'm going to go down and create a new table for our file handling. And I'll just insert one. And we saw for this, we start out with our logical name. Get side by side here with 75 things. So we saw that our logical name is going to be equal to our open and then our actual file and unload. So if we look at a statement like this, we did in file equals open ubdata.txt. So what we have there then is this logical name is a name that we can assign. So we'll make that blue and blue. And I want in file to be lowercase. Now the open is a keyword, so we can't change it. But our file name is going to be our actual file name in the system. That's something that is changeable. By us. And then we saw that for Python, our access mode could be R or W. I think we can make it A for append to add more to the end. So an example would be this one right here that we have. Is going to open the qbdata.txt file for input as in file. And again, if you want to color code those, and then the other things that we saw are closing the file. So we use that logical file name and we say we want to call the close function. So our logical name is that thing that we can assign. So like last time we saw with arrays, that this close function is associated with the actual file, logical file that we create when we open the file. Now we saw that to read data, we could do file name, logical name, dot read line. But when we read, we expect data back. So we need to have a variable set up to contain that data that we expect back. So let's call that variable equals. And then I'm going to make variable a different color. Now, we don't show that on the example side. You could put that in if you want, but to me it's not there because I can read a line whether I retain that data or not, right? That syntax is fine. I'm just not going to know what I read if I don't save what I read in a variable. Now we also could do read lines to get us all of the lines. And then we also said that we could use a for loop. So we can say for record file. And in that case, our file would be the logical name. I'm going to change that there. Match. And our record would end up being our variable. So as we process sequential files, it seems like there's a lot of different things that we can do, but it's really not too many. We can read them, open and close them, and use them in a for loop. Anything else do you want to put in there? Okie dokie. Now when we write out a file, like they just don't give us very much at all because it's really not that bad. So they're going to say, let's take our input file and let's create an output file that only has these quarterbacks' names in it. Okay, so I'm going to switch back to Adam. And it's working so good with reading and writing files. I'm so happy. It hasn't before. Now in this example, I want to create another new file. And this one we're going to write our file.py. Oops. Help me. Now, the first thing is we still have to open our file. And this is going to be our input file. We're going to read our QB data file that we've been working with. So we're going to put our R as our access mode. We want to read it. Next, we're going to read the first record. And this is kind of a normal thing because if we can't read the first record, if there's some sort of problem, sometimes we want to do some special processing. So we might see this first read be something a little bit different. For our example, though, it's just set up to initialize our loop. So they call it a line. Let's call it a record. And a record is going to be our input file, read line. We just want one. Now, while there are records, we're going to keep processing in a while loop. So while a record is just basically saying, while there's some stuff in there, if it gets all empty, then that test would be false. We can't read anything out of that record. Now, instead of items, I'm going to say our fields are equal to splitting up our record. And our output data line is going to consist of the quarterback's name, which is field 1, plus a comma, plus their last name, first name, last name, last name, first name. We're going to switch it. Now, we're ready to print that thing out to the screen. And then we're going to read in another record. After our while loop, we're ready to close. Now this should give us an output of all those names. Let's run it. Sure enough, I see all the quarterback names. We've switched their names to last name, comma, first name. Everybody okay? Now, let's say instead of outputting to the screen, we'd like to save this to a new file. I have my input file. Let's add an output file. We're going to open it, and we're going to call it QB names, not .text. And we want to open it with a write mode. So we'll be opening one for input and another for output. Now this time, every time we print a data line, let's write it to our output file also. And what we want to write is our data line plus our \n, so that the system knows that's a new line. Now I'm going to intentionally leave the close out because I want to show you what happens if we run this without closing our output file. There's my little arrow. Let's try it. Press F5. Right now, I do not have a qbnames.txt file. When I press F5 to run, I see my output, and now I should see my qbnames text file. Yay! I'm gonna try to open it. Oh, there it is. Looks good. It's people's names, just like I wanted. So it's almost like Python went ahead and closed it for me, huh? So it can be really hard to remember to close your output files, but we could run into data corruption. So I'm going to go ahead and say out file close. And there can be times where we don't even have to do that close, but it's still a good habit for us to get into cleaning up after we're done. Because sometimes it can be hard to remember to clean up after you're done, they do have the with statement. The with statement kind of allows us to create a block of code that depends on a data file. So I could say with in file equal open qbdata.txt, run all this body code, and then when I'm done, Python would automatically close the file for me. So here's an example. Here we say with open mydata.txt as MD. So that is going to be the same as saying MD equal open qbdata. So a little bit different syntax to make us a little crazy, but we can handle it. So with our with statement, we have to change things a little bit and say my data file is going to be MD. It's going to be mydata.txt. And I want Python to open it with my with statement. I'm going to print each row, and then, or I'm going to print out the actual file, sorry. Then I'm going to print each row. Let's run it. So when we print MD, it actually prints out this line about the file. Then it prints the 2 lines that are in the file, and then it tells us that it closed it. So pretty fancy. That with statement just takes care of opening and closing for us so that we don't have to. The thing is that once we're past our with statement, once we've dedented back, then that file is no longer available because it is closed and done. Ha, shoo. So I want to take a look at, we go back to the 120 to the table of contents. And what we're going to start on for our image processing is, let's see, they've got it buried in here. I've got to find it. .12, yes, that's it. Thank you. Okay, so 8.12, they start talking about this image glitching. But before we look at it, you should see what we're doing. Let's go check. And I'll do this again next time. Let's look at image glitches. So an image is a file, right? Said everything's a file, music, images, all of those things are files. And if I'm looking at a Photoshop file, then it has specific Photoshop control codes in it that tell Photoshop what to do. Like here's some red, here's some green, here's some blues, those kinds of things. Or I don't even know what kind of stuff Photoshop takes care of. But images are just files. So I want to look at images for not image glitcher, but image glitch. I've got things going everywhere. So I want to show images for image glitch. Here's some fancy ones. So image glitching is kind of a separate art form, and I thought we should end the semester doing some art form kind of stuff because we've been doing some console things. So here's some glitches. What image glitching is, or glitching an image, is taking an image and kind of altering it. So here we have a famous one, right? Kind of a statue that's been sort of smeared, you know, and spread across, and then some hearts added. See, there's some really good ones. There's a lot of Marilyn Monroe ones. There's a lot more than there used to be because we've been doing it. Oh, here's one that's cool. In this one, we have this image of this person, and it's kind of been glitched up a little bit where some certain areas have been like squared into colors, like a color block was added. But then I like this, it's cool because I was a hardware person for so long. This is the picture from a disk check when we're finding bad sectors on a disk. Shows these kinds of images like this. And so they took that disk check image and overlaid it over this image, and it's a little offset and stuff too, so that's pretty cool. It's kind of like music, you know, sort of making it your own. Let's find some others. This one's cool, just materials and fabrics and stuff that have been glitched up. Some of them are just more like somebody created a new piece of art. I like this one. We've got some squares and some different things. This one's cool, where we've got some hardware-based glitching. So that's sort of what it's like. Image glitch is like programmatically making it look like something went wrong, you know, like the computer sort of crashed there for a second and mangled the image or something. But it's kind of cool because you can take existing things and modify it to be yours, to be your own image glitch. So let's see what we have here. We're going to get this image library, C image, and make sure we've got a hold of it before we can do much with it. So let's go ahead and click next. Whoops. Let's go back to 8.11. And in 8.11, we have some explanation for what an image is. And an image is just basically a two-dimensional array, a matrix, right? A matrix of rows and columns, just kind of like a file. A file is just a bunch of rows and columns. And that's what an image is contained in a file. So everything all comes together. These things are all basically the same components. So here we have this matrix. And what we're saying is, if I want to change this pixel or this location in the image, I would need to go to row R, column C, and then I would be able to update that pixel, and that would change that spot in the image. So whenever I'm looking at an image, the intersection of a row and a column is going to be referred to as a pixel, right? A pixel is just a unit of color. Now, for each of those pixels, they hold a color. And a color, especially for those of you that have had the web dev class, you know a color is comprised of, at least on a computer, of the red and the green and the blue components. If we set all of the red, green, and blue of a pixel to 0, that pixel is going to display a black. The highest value a pixel can have is 255, because a pixel is 8 bits of binary, and we learned from our binary that 255 is the maximum value we can hold in 8 bits. So if I have each of those bits turn, or each of those bytes all the way on, red is 255, green is 255, and blue is 255, I'm going to display white. Okay, so white's all on, black is all off. Now, as I change the red, green, and blue intensities, I'm changing the color, right? So if I want something to be all red, I would have red set to 255, green and blue both zeros. If I want to mix them, then I can start mixing yellows and different things. Okay, so we know we have our 3 color codes that are used to create an actual color. Now, when we're working with our image model that we're going to use to process our image, to glitch it, it has a component called a pixel. So for each pixel, each row, column, intersection in our image, we can access that pixel using this image program. So for our pixel, we have some different actions that we can do. We can get the red component of that pixel, we can get the green component of that pixel, or we can get the blue component of that pixel. Then we could also use another method or function to set each of those. So they give us some example code here of how to figure out what a pixel's red, green, and blue values are and how to update them. Here's one. This one is just going to a specific pixel and setting its red to 66. All we're going to output from that are some numbers. So as we're working with images, our images are going to become objects. They are objects we're working with. Now here's the first image object we're going to work with. This image object is a picture of Luther College. I'm not sure where that is, but it's a college where one of the people that's involved in Runestone teaches, right? So we have this Luther JPEG, and we're going to use our image library to read in this image object. It's now going to be called IMG. And then we're going to print out its width and its height. We're going to get a pixel that's at location 4555, and we're going to print out the red, green, and blue values of that pixel. Let's try running it. Okay, so our image is 400 high, 244 wide, and the pixel at this location 45,55 is equal to those hex codes. And so we're talking about some looping going on through our rows and columns, which we'll look at on our own next time. But I wanted to get to this point where we can see what's going on with these 2 other images. Here we have, is he the LSU guy? And then Goldie the gopher. This image module does. So it tries to make everything really, really friendly, and it outputs in base 10. So it'll be super friendly for us, and we can just look at color codes to decide how we want to change it. So let's check this one. Here we're going to mess with Luther. And in Luther, we're going to find each pixel, and we're going to change each pixel by subtracting the current color value from 255. Let's see what happens if we run this. This is going to mess with the Luther JPEG. Let's see what happens. I'm going to run it. There's our Luther JPEG. And now, when we subtract the current color value from 255, what we're going to end up with is like a grayscale. So this will be kind of our first step in glitching our image to get it to grayscale. So there it goes, it's doing it. Is it grayscale, reverse video, inverted reverse video? Negative intensity. I'll say that. So yes. Negative intensity or reverse video. So there is some other things we could do to grayscale. So if we wanted to grayscale, we could average the red, green, and blue. Let's try that. We would have to calculate an average. Okay, so I'm gonna get all three of them and add them up. Add up those pixel values. And then I want to divide by 3 to get the average. But I need to make sure that's an integer, because if you've noticed, everything is pretty integer oriented here in our image library. Now, if I do that, I'm going to set each of these equal to the average instead of the value that we had before. So now our new, and I could just change this call down here to the new pixel and use the average in all 3 places too, either way. Oh, good. Isaiah's going to get super specific with glitching some images. That's what we want. Let's run it again. Okay, so here's our loser college. Is it going to work? Oh, there it goes. It was doing it so gradually I didn't even notice. So there we are getting a grayscale. Okay, Isaiah's okay with that one. So look through this, and next time we're going to make sure we can get that image library so that we can do this on our own using Atom instead of just doing it through the Runestone Academy setting. But they do have some good information here. Now, I want you to think about, what could I do? I could have, I don't know, I could have used excuse me, some sort of specific if statements, you know, and said if my row is greater than 45 but less than 57, you know, make it all purple or something if I wanted a purple stripe through my image. I could look for random rows and columns after I've looped through the whole thing and just randomly change pixel values to black or whatever we wanted to do so that we could put little spots and things. So be thinking about that, but you don't really need to do, you know, a whole lot of work. Keep practicing, keep looking at things, working on that. And next time we'll get it to work and get it all turned in. Make it all beautiful. Any questions before we go? Oh, how to find it? Okay.
No, thank you.
I'll show you, but I'm going to do it again next time because it's buried in here. So let's go back to that spot where they first mention it. Oh, okay. So you found the GitHub folder. Okay, so in 8.12, it says you can download it from the GitHub page. So I'm going to click on the GitHub page. Now, when you go to the GitHub page, we want image.py. And this is the easiest way to do it. It's pretty dumb. But I'm going to open image.py, and I'm going to look at the raw code. And I'm going to Control A to select it, and Control C to copy it. Then in Atom, I'm going to create a new folder. Image glitch. And in my new folder, image glitch, I'm going to create a new file. And I'm going to make sure to name it exactly the same as they have this comment up here, image.py, all lowercase. And then I'm going to paste that code from GitHub. And I'm going to close it because I am not going to change that at all. And if I get an error in it, it's going to be from my code, not from theirs. So just image.py, yeah. And if you start manipulating pixels with image.py, if things aren't just right, you can get an error, and it looks like it's something wrong with their code, but it's the way the data is being passed to it, so we can usually figure out a way to handle it. But it's definitely a simple image processing library, like they say. So it's not a super fancy one. Now, once you get the C image, if you go to the Runestone Academy, which I think I closed. And you guys, I'll show you this next time. So if you're wanting to wait, you sure can. So I don't want you to be feeling like you have to rush, because we'll be doing all of this next time. Where was it? He showed me. 8.12. Thank goodness you guys are keeping me on track. Now, if we go back, I would go all the way back to one of the first examples. I keep thinking that I need to go forward, and it just keeps going down. The example that you probably want to copy is this one right here that uses the Luther image. Now, a couple of caveats. Because our image.py is kind of a simple image processing, even though it says this is a JPEG, we need to find a, what does it say? You have to find a certain type file. You just really are going to have a lot better, sorry, it doesn't have it there anymore, but you're really going to have a lot better luck if you use a GIF. So just some sort of animated file, animated image file. It's just going to grab one of the animations and use that to update, but for some reason it seems to work better. Okay, so we'll do all that next time. Isaiah, send me a message if you run into any trouble. Anybody else that's trying it, just send me a message and I'll get you all moving along. But I don't want the rest of you thinking that you need to worry about that right yet, because we'll get it all going next time and do some experimenting. Great, we're almost done. Any other questions? You guys have just done a great job. I'm gonna go ahead and end this thing. Happy Tuesday. See you on Thursday.